Okay, so in this video, we're going to look at the, instead of looking as we did in the previous video at the displacement of a pendulum at a specific point, we're going to look at the velocity of a pendulum at a specific point. So here's their amplitude, here's their equilibrium, here's the amplitude as well. And say we want to find out what the velocity is at, say, this point right here. At a displacement of x, or at a time from that equilibrium point, or as you may be already aware, at a time from the amplitude. And we'll look at some equations on how we can actually get that and how we actually get those. One thing you need to be aware of is that at the amplitude, the velocity is 0. Okay, for a very instantaneous second before it starts moving back on itself, but the velocity is 0. At the equilibrium, the velocity is the max. And at the amplitude, again, velocity is 0. So we keep switching between those as we go backwards and forwards. So let's look at our circle again of this situation. And again, we've got our amplitude here. We've got our equilibrium here. Amplitude again here. And equilibrium again there. Now, oftentimes in the previous video, some of you might be thinking, well, what about the rest of the circle? Well, yeah, it's just the same thing. So as we go from here to there, that's from there to there. As we go from there to there, it's there to there. As we go from there back to there, it's there back to there. And from there to there, it's there back to there. So that's how the simple harmonic motion works with the circular motion. But let's look at this now from the perspective of velocity. Well, we've already said that the velocity is maximum there, and I'm going to leave that Vmax there because it's the same for the equilibrium. And so we can actually use this circle, instead of representing positional analysis, we can represent this size of this arrow represents a maximum velocity. And the size of the arrow as along this axis here, well, there's no vertical arrow at this point. We could create triangles, and I'm going to create a triangle here, where the velocity of this one is this arrow here, and notice that it's smaller than this one. If I was to draw an arrow going across here, you could have a velocity that was that big. And obviously, if you got to the amplitude, what do we know happens at the amplitude? Well, we have a v of 0 because there is no vertical velocity. So we're actually now looking at this side of the triangle to work out what the velocity is. Remember, this side is Vmax. So where it's the largest, it's Vmax. Well, we can use the same kind of thought process as before. We can say that the angle from the equilibrium is theta. Okay? Which means that that angle there is also theta. Which means that that angle there is also theta. And now we're back to the same old trigonometry as before. We want to know what the size of this side is, because that is going to indicate our velocity at this point. So we have our velocity that we want to know. We'll call that v. And we have this side of the triangle. Now, what's interesting about this side of the triangle, notice how long it is. It's the same length as this one. It's actually the same length because it's the length of the radius of this circle. So actually this value represents V max. So that is a maximum velocity that's there. So for all intents and purposes, we can now say, we can draw a trigonometric relationship between these values. This is the adjacent, this is the hypotenuse. So yep, we're using cos theta equals the adjacent over the hypotenuse. In this case, we can rearrange for the adjacent. So adjacent equals cos theta times the hypotenuse. And now we can swap out for the values that they're meant to be. So A is the velocity. cos theta times by the h, which is V max. Now, as before, some terms are used differently in different specifications. Sometimes Vmax is represented by the letter V naught. So just be aware that you might have a specification that the maximum velocity is represented by V naught in this case. So then, where do we go from here? Well, we can write V equals Vmax cos theta. Or, as we said from before, theta can be replaced by omega t. Now, really importantly now, we're going to make this statement at the beginning. This is the equation when the time, this time here, is the time from the equilibrium. Because remember in the previous video we had two equations, one from the equilibrium, one from the amplitude. For the velocity at this point, we have got Vmax cos omega t time from the equilibrium. Well, some of you might be thinking, well, okay, I see that, but where do we get rid of this Vmax? Because I don't have the Vmax value in my equation sheet. What you might have is it might say omega x naught. Well, or omega a. And where that comes from is actually from another equation, which I'm not going to derive here. But it comes from the fact that the velocity can also be worked out using the following equation. Okay? Now, one thing you can observe at the amplitude, where Vmax is going to be the case, what do you know? Well, Vmax is at the equilibrium point. Then in this equation, this value is 0 because the displacement is 0. This is just the value of what the amplitude is. So we can get rid of this term because x squared, if x is naught at the equilibrium point where velocity is max, then we can get rid of this term. So I'll write that if Vmax x equals 0. So we can get rid of that value. So we end up with V equals plus or minus omega x squared square root. Remember, x naught is the amplitude. So we could replace this with the amplitude should you wish. I'm going to use x naught for the purposes of this video. So V is equal to omega x squared square root. Well, if you square root a square number, all you end up with is just the value. So V is equal to plus or minus omega x naught, which x naught is the amplitude. Remember, omega is the angular velocity. So the velocity max is omega x naught. And we can now use this equation into this one to make a final version of this equation, which will be V equals omega x naught cos omega t. And again, you could swap out the omegas with 2 pi f's and whatnot, but for all intents and purposes, this works. So where V is equal to omega x naught cos omega t. And this works really well for determining, remember, the time from the equilibrium, the velocity after that time from the equilibrium. This is the equation. That's where we get it from. But there's another equation, isn't there? And hopefully you'll notice and you'll be looking at your equation sheet and say, yes, there is another equation. Well, there is another equation for this, yes, from the amplitude. So I'm going to use a new piece of paper for that one. Okay, so again, we've got our circle. I've got our equilibrium point, we've got our amplitude, and we've got our position that we want to know the velocity of. And again, we still want to know what the height of this is, because that is going to be our velocity, where this is a maximum. But remember, this time we're going to look at it with the angle from the amplitude, theta from the amplitude. So with theta from the amplitude, we have now got a very different equation. We've got the opposite hypotenuse. And I'll remind you, sine theta equals the opposite over the hypotenuse. So sine theta times the hypotenuse equals the opposite. We swap all these round for their proper terms. We have V is equal to H is the V max, sine theta, V is equal to V max sine omega t, because remember we can swap that out. Now, some of you may be realizing, looking at your equation sheet and going, okay, well, we can swap that out as well, and we have omega x naught sine omega t, and that works perfectly fine. Now, just to make it very clear, this is the time taken from the amplitude. From the amplitude. So you're working out this velocity at this point based on the time taken from the amplitude, not from the equilibrium. The previous equation was from the equilibrium. This one's from the amplitude. So we've already explained where all these values come from. But there's one more thing to pay attention to. Now, think about this in terms of the graphical representation of what's going on during simple harmonic motion. So I'm going to draw two axes here, and I'm going to do my best to draw these well. So I've got two axes. This will be the displacement time, and this will be the velocity time. And so, since our displacement for this one starts at the amplitude, we can draw a nice wave like this. Starts at the amplitude, goes to the other side, go back to the equilibrium, back to the amplitude. Well, what is the velocity doing at this point? Well, it's going to be what the gradient of this is doing. So if s is here, there's no gradient, so that must mean that the velocity is 0, okay? Because it's not moving at this point, it's a flat top. This point here, this is a really fast speed or a very fast velocity because the gradient is the greatest at this point right here. But notice, what sign am I going to give it? Is this a negative or a positive gradient? Well, it's a negative gradient. So this means this is a negative velocity. So if I plot points down here, we've got that point there. Again, up to here, we've got 0 velocity, because at this point it's not going to be moving. Now we've got a positive gradient that's very, very steep. So we've got our highest positive velocity, and then back down to 0. And we can actually then join up the dots. Now you can also do this for acceleration, which is the gradient of this graph and on here, and I might do it in a little bit just to show you, or it might be in another video. But for all intents and purposes, what you can see here is that when the displacement is positive, okay, which we can start off with a positive displacement, it means this is a negative velocity. So it actually means we need to add a sign to this equation because at the moment it's not correct. We need to add a minus sign. So that minus sign is there on this equation only because when the displacement is positive, the velocity is negative. And that works really, really well to explain where that negative comes from. Interestingly enough, you could apply the same logic to the previous equation, which I can actually go back to now. I've left some space for it specifically. So I'll put a sheet of paper under there so you can see it without seeing the underneath paper. So this is back to the original equation. This is fine as it is because this is positive. Let's draw those graphs again. Displacement time, velocity time. But this time, because we're going from the equilibrium, we start like this. And again, we can use the same logic as before to say, oh, well, I've got a very high gradient right here, so I'm going to have a very high positive gradient, so a very high velocity. Here, I've got zero velocity. Here, I've got a very high negative velocity. Here, I've got no velocity. Here, I've got a high positive velocity. So we can draw the following. And look what happens. When I have a positive, displacement, look what I have. I have a positive velocity. Hence why this value is positive. And it also gives context to why this equation is also plus or minus the velocity, because it's not taking into account whether it's from the amplitude or whether it's from the equilibrium, but works in both cases. So this equation at the top here is the velocity equation. You can find that derived in your book. It's actually quite a complicated derivation, but it's not too bad. You can get your head around it. But if you can accept that the velocity is equal to this value, then all of these other equations follow suit quite nicely and explain why this is a positive and this is a negative one. So we'll end there with this video because it's gone on long enough. Hopefully you found that useful as explaining where those equations come from, and we'll see about some more simple harmonic motion in a video or two's time.